NASA's Parker Solar Probe reveals the birthplace of solar storms. In a historic milestone for heliophysics, NASA's Parker Solar Probe has ventured deeper into the Sun's atmosphere than ever before, capturing unprecedented images and data that illuminate the chaotic origins of the solar wind. Skimming just 3.8 million miles from the Sun's surface, the spacecraft has provided humanity with its closest view yet of the solar corona, the birthplace of solar storms that shape space weather and influence life on Earth. If you like my content, then subscribe my channel, and don't forget to like and share this video, unveiling the mechanics of the solar wind. The solar wind, a continuous outflow of charged particles from the Sun, has long been a subject of intense scientific inquiry. Now, Parker Solar Probe's latest flyby is offering definitive insights. Using its wide-field imager for solar probe, WHISPER, the spacecraft documented dynamic interactions between coronal mass ejections, CMEs, twisting magnetic fields, and the heliospheric current sheet, the sprawling boundary where the Sun's magnetic polarity flips. Parker Solar Probe has once again transported us into the dynamic atmosphere of our closest star, said Nikki Fox, Associate Administrator for NASA's Science Mission Directorate. This mission allows us to witness, with our own eyes, the very regions where space weather begins, enabling a quantum leap in forecasting solar activity that could affect astronauts, satellites, and electrical infrastructure on Earth. A closer look at space weather engines, the WHISPER images reveal stunning new details about CMEs, massive eruptions of solar plasma, merging and colliding near the Sun. These interactions are critical to understanding how CMEs accelerate particles and distort magnetic fields, potentially amplifying their impact on space-based and terrestrial systems. In these images, we're seeing CMEs stacking atop one another, explained Angelos Vorlidis, WHISPER instrument scientist at Johns Hopkins Applied Physics Laboratory, APL. These observations help us decode how CMEs combine and evolve, essential information for modeling space weather events. The probe also observed the heliospheric current sheet in unprecedented resolution, shedding light on a key structural boundary in the solar wind's propagation. Such observations are refining our understanding of how magnetic field configurations influence particle flows across the solar system. Tracing the origins of the solar wind. The solar wind, first theorized in 1958 by the late heliophysicist Eugene Parker, for whom the probe is named, has long been observed from afar by missions like Mariner 2, Helios, Ulysses, and ACE. However, Parker's solar probe is the first mission to directly sample and image the solar wind within the corona itself. Data from its earlier orbits revealed the presence of abrupt magnetic field reversals, or switchbacks, at distances as close as 14.7 million miles. As the spacecraft descended further, scientists traced these switchbacks to specific magnetic funnels on the solar surface. In 2024, researchers linked them to the fast solar wind, partially solving a mystery that has persisted for more than 5 decades. The enigma of the slow solar wind. Yet the slow solar wind, traveling at roughly 220 miles per second, remains less understood. It is denser and more variable than its faster counterpart and can generate geomagnetic storms when interacting with other solar features. Parker Solar Probe is now providing valuable clues. Prior to its flybys, remote observations had suggested that 2 distinct varieties of slow solar wind exist, one with switchbacks, alphanate, and one without, non-alphanate. The probe's close-up measurements confirmed this bifurcation and offered insights into their likely origins. Scientists now believe alphanate slow wind may arise from coronal holes, regions of lower density and temperature in the corona. Non-alphanate slow wind likely emerges from helmet streamers, looped magnetic structures over active regions. Understanding these origins is vital, as the slow wind plays a complex role in shaping near-Earth space weather. The Parker Solar Probe will continue gathering data during upcoming passes, including a pivotal approach on September 15, 2025, that may finally reveal the full picture. Toward a predictive solar science, unraveling how the solar wind is generated and how it escapes the Sun's gravity is one of the grand challenges of heliophysics, said Noor Rawafi, Parker Solar Probe project scientist at APL. Thanks to this mission, we are closer than ever to understanding the Sun's invisible forces and their reach across the solar system. With each orbit, Parker Solar Probe is not just deepening our knowledge of solar dynamics, it is building a foundation for more accurate predictions of space weather that could protect astronauts, spacecraft, and power systems on Earth for decades to come.